How you guys doing? So we should talk a little bit about the lab. I'm starting to wonder how to make this lab work most efficient. And my experience from yesterday's lab was that we really, these labs, the majority part of it is about wiring. And I want to make a strong suggestion that when wiring occurs, if there's one person wiring in that group, everybody has to be looking at the wiring simultaneously. Everybody has to be problem solving on how to wire that circuit. So the idea, I think, is that we have to change what we're doing. Right? This is a new online world, and I don't know how do you do this in a circuits class. So I'm thinking you each have your own board. Even if you don't have a power supply, you should each be wiring, and somebody should be piece-spicing the result. When the wiring, if you guys all show the same wiring, and then you go to wire it up and apply power to it, and if you get the value of the piece-spice, then good. But my experience is that that's not what's going to happen. So what happens here is that you all have to be the wiring, not one person. And I know what I said yesterday in lab is I said, you guys can split the duties here. But the whole point of all of this equipment is that to get you to wire, period. Even if you don't have a power supply, you should be wiring it on your board to try to get a sense of what's going on. Because more than likely, you're going to be experiencing wiring problems. What happens here is that these labs are set up as group labs. And if only one person is doing the wiring at this early stage of your circuit experiences, you're going to get your butt kicked. Because let me tell you, next week's lab is ruthless. There's no doubt about it. You have to work in groups. You cannot work by yourself, because then it's like you doing the lab all by yourself. So if you're working this in groups, that means everybody has to be looking at the wiring simultaneously. I know I'm repeating myself, but that's the reason why I worked my ass off to get you the equipment, because by you wiring, you learn the material better. I have experience where that wasn't the case. Okay, so from now on, I'm hoping that starting on Friday, starting next week, we all start to do the wiring first. Focus on the wiring. And then once that happens, then somebody is powering it up, somebody is piece-spicing it, somebody is checking it. Only after that should calculations even be thought of. Okay, let's move on. So we're talking about mesh analysis. And in mesh analysis here, what we were doing here is that we started looking at, we started with voltage sources as only. And here's the sort of like, for each loop, you assign a current loop, and then you determine the number of unknown loop currents. The number of unknown loop currents has to equal the number of the equations. So you have equal amounts of equations and equal amounts of unknowns. Then you apply the loop equation to each unknown loop current. So that means that it's the sum of the resistors connected to loop 1 minus the sum of the mutual resistors connected to loop 1 times their currents. And then there's this plus or minus voltage source. The sign convention, remember, the sign convention is for the constant sources on the other side of the equal sign. So if the current comes in to the positive end, I then take that KVL term to the other side and it becomes negative. When I see a minus sign, I take it to the other side of the equal sign and it becomes positive. Then we solve for the appropriate loop currents and the appropriate variables. And by the way, there were some people on Tuesday yesterday, that felt that maybe loop currents weren't real. They're real, without any doubt. When you measure them, they are absolutely real. So here we go. So now what do I want to start on? I want to go in. I want to look at node analysis, mesh analysis, where now we're going to add current sources. So here we go. So what we're going to do here is that, very similar to before, is that when current sources are present with mesh analysis, the location of the current source tell us there are two types of current sources. So one of these current sources is if you have a current source that is isolated from other loops. And that forms a very specific current source in mesh analysis. However, if you have a current source that is connected between two loops, then we deal with this thing differently. In other words, what we have to do here is that we have to modify mesh analysis when a current source is connecting two loops together. So let's go look at this thing. So what I have here is I have an example circuit. And so when I look at this example circuit here, what I did here is that I set up two current sources, one that's isolated and one that connects two loops. So check this out. So here's one. And then I have a series of resistors. And now I have a second current source. And what you're seeing here is that you're seeing that I have a current source that's independent. And what I mean is it's not connected to any other loop. And you could see here is that if I look at this guy right here, I'm going to call loop 1, and you could see that this loop here has a current source in it, but it's not connected to, let's say, loop 2 here or loop 3 here. But you're seeing that there's a current source that connects loops 2 and 3, but one is isolated. So that's what we want to focus on. So what we're seeing here is that what we do here is that we immediately say that from mesh analysis, if I do step 1, we do the counting. And of course, we see the number of loop currents. So the number of loops in this case is 3. So this would imply that we need 3 loop equations. right? So the number of loops are 3, a loop equation, so we should have 3 unknowns. And these unknowns are I1, I2, I3. So, but we immediately notice that there are 2 current sources. So let me move up here. So, however, there are 2 current sources. So the first one I want to look at is that I want to look at the 10 milliamp source. When you look at the 10 milliamp source, what you're seeing here is that this source is isolated. And if it's isolated from the rest of the loops, then it forces that current to be whatever it is. Now note that I purposely put my current 1 to be in the opposite direction here. So what this does here is that this implies here is that then it immediately determines the value of the loop current. So in this case, we can clearly see that the loop current is 1. So it immediately tells me that this loop current must be 10 milliamps. So we now know what that loop current is. And note, I1 is in the opposite direction of the current source. So right away, what we're seeing here is that the number of loops, right? The number of loop equations, which was equal to 3, is now reduced by 1 because of that current source. So this tells us then that we have 2 unknown loop values, which is then going to be I2 and I3. So we've now reduced it. But then we noticed our second loop 1, and this is our 20 milliamp source. And what we're seeing in this case here, that 2 and 3 are connected. And very similar to a supernode, this loop now becomes a superloop. Okay, so what we're seeing here is that this current source connects loops 2 and 3 such that I2 and I3 are dependent upon each other. And what do I mean by that? Well, when you look at the source here, what you're actually seeing here, let me bring this guy down here. When you look at the source over here, one of the things that you see here is that I want you to focus on the branch of the current source. Okay, so we want to focus on the branch of current source. And what you're seeing here is that you have this guy that looks like this. Now, if you look at I2, look at the direction of I2. I2 is going straight down. If you look at the direction of I3, look at the direction of I3. It's going straight up here. So this is I3, this is I2. And if you look at this thing carefully, by the way, we can also do it slightly different, but this is the way I look at it. It tells me here that then I3 minus I2 must be 20 milliamps. In other words, I can write this. If I know I2, I automatically know I3. You know, another way, if this is uncomfortable for you, you could also do the following thing here. You could go in and you can also apply KCL to this node right here. If you apply KCL, note that I have I2 coming in. I have I3 going out. And clearly, if I apply KCL, if you apply KCL, you're going to get the same condition right over here. Okay, there's multiple ways of doing this thing. I find that it's more cumbersome to look at nodes, and it's more useful to look at this actual value right here. So let's do this here. So what do I want to talk about? When we get dependent variables, this forms a special situation called a super loop condition, or a super loop. It's called a super loop. And a super loop essentially says this, that these two, instead of having one loop, excuse me, instead of having two loops, you really have two loops together. In other words, this forms a super loop. And this super loop, again, done by a dash line, tells us how 2 and 3 are dependent on each other, right? And so the super loop here is essentially this dashed enclosed loop that shows the dependence. The dependence in this case of I2 and I3. So what that does here is that that second current source really reduces the number of loop equations. So this second current source reduces the number of loop equations to solve. So in this case here, you're seeing that we went from 3 to 1, where this guy was the 10 milliamp source, and now we are reducing this guy by the 20 milliamp source, which now gives you one loop. But it's not just a regular loop, it's a super loop equation. And a super loop equation essentially tells us is this. It tells us that we write two loop equations into one superloop equation. And that's exactly what we did with a supernode. A supernode takes two node equations, writes them into one to show you that they're connected. And then along with every superloop, there has to be what? A supercondition. With every superloop equation, there is a supercondition. And in this case here, that supercondition tells us this, which shows how I2 and I3 are dependent upon each other. So in this case, it would be I3 minus I2 equals 20 milliamps. That would be my supercondition here. So if I'm looking at this, I have a super loop, and associated with this is a supercondition. So what I want to do here is that I want to go in and I want to then show you how mesh analysis is modified then. Let me grab this thing here real quick. I thought I was set up, apparently not. So this is right out of my notes, and I want to share this with you. So here we go. So when I have a super loop, in other words, when I have current sources when I'm doing mesh analysis, it reads something like this. So it's very similar to what we've already talked about. And what we're seeing here, it looks something like this here. I got to find my mouse here. So what you see here is that if I have current sources and voltage sources, it goes something like this. For each loop, assign a current loop. And you know what? I would define the polarities. I wouldn't define the polarities anymore. Determine the number of unknown loops. That means count the number of loops that you would see, and then subtract the number of current sources that you see. That gives you the number of loop equations that you got to solve. Step 2, apply the loop equation to each unknown loop. So if I have loops that are independent, that means that there's no current sources in there, then I apply the regular loop equation. That is, it's the sum of the resistors connected to loop 1, the sum of the mutual resistors are subtracted, and then I have my plus or minus source. If there's a current source that is not isolated from the loop, then that current source connects those two loops and forms a super loop. And we identify that by that dashed enclosed loop. These two loops then must be written in a super loop equation plus the supercondition. So that means I look at the loop equations for loop 1 plus the loop equations for loop 2. And then if I have 3 loops that are connected, then I would put a third. But it depends on how that happens here. And then with that, I apply the super condition that connects those two values right there. So what I want to do here is that I want to go in and I want to do an example. Okay, I want to do an example. So let's check it out. So here we go. So what you're seeing here is that we want to go through this process here, right? I'm going to go through this process right here, right with you. And they're very, very similar to node analysis. So here we go. So example 3.5 says, find the current I1, Vx, Vz using mesh analysis. Okay, here we go. Step 1. So the first thing that we're going to do in step 1 here, we want to do the counting to determine number of unknowns. Right? When I say let's do the counting, we're trying to determine that. So you can clearly see that we have 3 loops. So therefore, what we're going to say here is that I have a loop here, right? I got loop 1. Why did I call this one loop 1? Because look at the current I1. That loop is already defined as I1. So why have a new variable? Then I'm going to have loop 2. And then I'm going to have loop 3. So right away, I see that I have that the number of loops is equal to 3. Now I count the number of current sources. When I look here, I see that I only have 1 current source. So I'm going to subtract this current source, right? So I only have 1 current source. So therefore, this tells me that I have 2 loop equations. Now, what I'm going to ask here is that where is that current source located at? Okay. And where it's located at is it's located at where? In between 2 current loops. 2 current loops. So what you're seeing here is that right away, what I'm showing here is that I have a regular loop. That regular loop is I2. That loop has no current source, so I have that. But then when I focus on that current source, what you're seeing here is that I have a super loop. What super loop? You could see that the current source connects what? I1 and I3. But with every super loop, there's a super condition between I1 and I3 here. Now, let's look at this thing here. We have to solve for I1. Okay, we have to solve for I1, but note, loop 1 is also I1. So when I solve for I1, I automatically get I1. So I don't need a solver for I1. Now let's go look at the loop Vx. When you look at Vx, it's across the resistor, the 1K resistor. So I'm going to start to say here that I'm going to look for what? Solver equations. So when I look for solvers, I'm going to need the loop for Vx, and I'm also looking for Vz. So the way it stands here, what am I actually seeing here? I'm seeing that I have what? I have 1, 2, 3, 4, 5 equations. So I have 5 unknowns, which is going to be I1, I2, I3, Vx, Vz. And therefore, I have to generate 5 equations. So you better have 5 equations. Let's go do this here. So what I'm going to do here is that I'm going to start with the regular loop. Okay, so I'm going to go to loop 2, and I'm going to start looking at that. So when I look at loop 2, let me go get this this loop here so it's easier for us to write it down. So what we said here is that we have loop 1, we have loop 3, we have loop 2. And what we said here is that when I'm looking at these things here, we said that we had a super loop. So I got to go indicate the super loop. So when I'm looking at the super loop, what I'm seeing here is that the super loop is where? Along here. So this is my super loop that connects 1 and 3. And then clearly I have a second loop in 2 right here. Let's start with loop 2. So here we go. Loop 2, I'm going to go around and I'm going to go, let's count them here. So I have 1, 2, 3 resistors. So for loop 2 here, I'm going to have 10 plus 1 plus 1 times I2. Look how I dropped the K's. No kiloohms. So when I write out the milliamp sources, I'm not going to write the milli. I'm dropping the K and the milli symbols. So then, are there any mutual ones? Yes, there is. There's what? There's 1 for I1, and then there's 1 for I3. Are there any voltage sources in the circuit? The answer is no. I have loop 2 now. Let's go to the super loop. So now I have super loop 1 and 3. So here I go. I'm going to start off with loop 1. How many resistors do I have in loop 1? I have 1, 2. So here I go. I have 1 plus 1 times I1. Are there any mutual ones? There's a mutual one with 2. There's a mutual one with 3. So then I'm going to go minus 1 I2 minus 1 I3. Okay? So this tells me about what? Loop 1. But a super loop says I have to write 2 loops in one equation. Now look at loop 3. How many resistors are connected to loop 3? There's 3 of them. So then I'm going to go to 3 and I have 1 plus 1 plus 1 I3. Are there mutual ones? Yes, there's 1 connected to I2 and then there's 1 connected to I3. Are there any voltage sources in this circuit? Yes, look at the direction of the blue loop. I hit the minus sign for the 10. I take it on the other side of the equal sign, and I'm going to get what? I'm going to get 10. But you know what? I'm going to move this over a little bit. I need the space over here. Okay, I want to move this.
Hey, Carlos.
Yes.
That last term, should that be minus 1 I1?
Yes. Thank you.
Yeah.
And that should be 10 right here. So note that this guy here is loop 3. Okay, that's my super loop. But with every super loop, there has to be what? A super condition between 1 and 3. So then I go to where the current source is at. Look at the current source. So the current source looks like this. And then look how 1 goes straight down, right? 1 is going this way. 3 is going the opposite direction in that. So when I look at that, you have to focus on the direction of that. So this should be I1 minus I3 has to be 1. But remember, I dropped that. There's my super condition here. Now let's go look at the solver equations here. So when I look at my solvers, I'm looking for the solver for Vx. So I got to go to where Vx is written here, right? Let's make this a little bit bigger to see if I can make this a little bit. Oh, damn it. Let me see if I can get that to work here. Not really, huh? Okay, never mind. But what you're seeing here is that look at Vx. Vx is connecting 1 and 2 and 3. So let's go look at Vx. So what you're seeing here, here's Vx. And look at the polarity of Vx. Now look at the directions of the currents. I2 is going which direction? I2 is coming this direction. I3 is going what direction? So you could see that the I3 is entering the positive node. So then I'm going to write Vx according to Ohm's law should then be 1 times the currents. So it should be I3 minus I2. But then I'm going to put that into matrix form. So this is going to be I3, I2 minus Vx equals to 0. That's my solver here. Now let's look at the solver for Vz. Look at how we have Vz. See what's special about Vz? What's special about Vz? Do you know the value of Vz? Yes. Look at the current source. It's in series with the 1K resistor.
So it has 1 milliamps.
1 milliamp. So what's the voltage across that? What's Vz?
1 volt.
1 volt. So therefore, because current source in series with resistor, that implies Vz must be 1 volt. So what does that tell me? I don't need to solve for Vz. I already know it. Okay, I don't need to solve for Vz. I already know it. So that means then, instead of 5 unknowns, I have 4 unknowns and 4 equations. So you could see that, what am I going to do with this guy? I don't want that equation. I already know the answer. Could I have written it? Yeah. So let's matrix this thing up here. So what we're going to do here is that we want to matrix this guy up. Do here is then again I'm going to do I1, I2, I3, Vx, and then I have my constants. And you're going to see that I'm going to modify this in a little bit here. So what you're going to see here is that if I come into this equation here, look at my I1. Here's I1 right here. Here's I1 right here. I1 right there. No I1. So then if I go to the next one, I2, I2.
There's an I1 in loop 2 as well.
Yes, there is. Thank you for the help. And if I look at I2, there's one right here. Now I'm going to go to I3. And then finally, there's only one Vx, which is right here. So then I'm just going to go in and I'm just going to start writing these things up. So the first one has -1. You could see that this guy's -1, -1, and you could see that 2 here is going to have 10 plus 1 plus 1. 10 plus 1 plus 1. And then Vx, of course, is 0. And then if I look at my sources in this case is 0 for loop 2. Then I'm going to keep going on. So if I go to the super loop, I have, look what I get. I get 2 minus 1. So that immediately gives me 1 for I1. And if I look at 2, you're going to have -2, -2. You could see I'm going to get -1, -1. And then if I go to 3, I have 1, 2, 3, -1. That's going to give me +2. And then this is going to give me 0. Then I look for my constant term, which is 10. Now, let's look at the super loop equation. You could see I'm going to get 1, 0, -1, 0, 1. Then I look at my solver equation. I'm going to get 0, -1, +1, -1, 0. So here are my 4 unknowns. And they look like this. So what am I going to do? I'm going to go in, matrix magic. And when you compute this, this is what I end up getting. I get I1 is 4.44 milliamps. I2 is 0.656 milliamps. I3 is 3.44 milliamps. And Vx is 2.78 volts. So then what was I looking for? So if I come back up here, my goal was to calculate I1, Vx, and Vz. We already figured out that this was Vz right here. So here's I1, and then here's Vx. So I now have all of the variables that I needed to compute. Okay, any questions about what I just did? Okay, there's no questions. We go to the last part of the chapter, dependent sources. So now we're going to talk about node and mesh analysis Okay, let me organize here. When there are circuits that have dependent sources, we treat a dependent source exactly like any other source. However, just like we saw in chapter 2, anytime you have a dependent source, there's a dependent condition that comes along. So when dealing with circuits with dependent sources, treat them like any other source. There's nothing special about them. However, each dependent source has a dependent condition, right? That's the so-called DC. And this DC must be written in terms of node voltages or loop currents. So if you're using mesh or node analysis, you have to rewrite. So this is what we got to do here. So the process goes something like this. You apply regular node / mesh analysis. So then if the circuit contains a dependent source, so if a circuit contains a dependent source, we must apply a DC. So then we go through this process here. So you got to go to the controlling element, must be defined in terms of the way we say this here is that we say node voltages in node analysis or loop currents in mesh analysis. So you have to do that. Now what you're going to find here is that we're not going to step it up now. In the past, when we defined these guys, we have typically been using Ohm's law to actually do it. Guess what? Not anymore. You guys are all grown up now, right? So we want to treat you like grown-ups. So that means you're going to see KCL, you're going to see KVL, which complicates circuit solving more. So to give you a sense of what I'm talking about, I want to go look at some simple example circuits to give you a sense of this. So let's look at an example circuit with node analysis. So what I want to do here is that I want to give you this nice circuit that you could take home and show your significant other one if you'd like. And what you'll see here, that it looks something like this here. And what you're finding here is that I have a 4K here, I have a 2K here. And what I'm seeing here is that I have a current controlled current source. So this guy is a 5IX. And my 5IX is right in here. So we can see this thing here. So let's do the counting. So if I'm using node analysis, that means we want to count nodes. So let's go look at this thing. I'm going to set my ground. So I think this is a good choice for the ground. There's my ground. Now note, one of these nodes I already know, right? That's got to be 2 volts because it's the voltage source connected to the ground. So the only unknown node voltage that I don't know is this guy right here. So what am I going to calculate? Call this guy? How about if we call this guy Vy? So what you're seeing here, if I do the counting, that tells me that I have 2 nodes minus 1 source. So I have 1 node equation. So then I ask myself, is this voltage source connected to the ground? The answer is yes. So that is a regular node thing here. So this tells me here that I have 1 node, Vy. So I have a regular node, which is then Vy. So it's not a super condition because the ground is connected. I mean, the source is connected to the ground. But then I see that there's a dependent source. Because there's a dependent source, I automatically have to add a DC for Ix. So in order to solve this equation, I have to write a DC thing here. So when I look at this thing here, I have what? I have 2 unknowns. So I have Vy and Ix. So I need 2 equations. So when I go and I look at this thing here, what you're seeing here is that when I write this out, I have my node equation for Vy. And if you look at this, if I write this out, this is the green node, of course. So I could see that I have 2 resistors. So if I write this out, I'm going to get a fourth, a half, times Vy minus mutual. 2 is with 0. 4 is with this guy. So this is going to be 4 times 2. And then look at the current source. The current source is flowing into the node. So therefore, this is a 5Ix. So look at what I did with the node equation here. What you're seeing here is that I have Vy as an unknown, Ix as an unknown. So one node equation gives me 2 unknowns. So this is an unsolvable problem. So what does the DC do? It gives you the second equation. So now let's go look at the second equation here. So what you're seeing with the second equation is that I got to go write my DC here. So this is my DC for Ix. So here I
Hey,
go.
Carlos,
Yes.
shouldn't that be minus 1/4 times 2?
Yes.
For the,
Thank you.
okay, cool.
It should be thanks for the help. And so now that DC, I go to where it's defined. And you can see that it's defined across the current through the 4K resistor. So if I look at that 4K resistor, it looks like this. And I can see that the current is flowing in that direction. And of course, this node right here is the 2 volts. And then you could see that this other node right here is Vy. So when I look at this, I'm going to apply Ohm's law, and I'm going to rewrite Ix in terms of the node voltage. So therefore, my DC then should be 2 minus Vy. And since this is a 4K here, this is going to be 4Ix. So now I have a system of 2 equations and 2 unknowns, right? I have a second equation with Vy and Ix. Now this is a solvable problem here. That's how I apply the DC right here. Okay, so what I want to go do now is I want to go to the next circuit here. Here we go. So I want to go in and I want to apply node analysis to this circuit here. So let's go look at this guy. So it says, example 3.6 says, determine the voltage Vx for this node circuit. Okay. Where would you put the ground? Where's a good place to put the ground at?
On the bottom by the like 4-volt one.
Okay. You're saying right here?
Yeah.
Okay. So one suggestion is to put the ground right here. Any other suggestions?
We put it on the right-hand side where the 2 voltage sources are.
The other one is here.
Oh.
And you could put the ground anywhere you want, right? You could also put the ground right here. Or, you could put the ground anywhere you want. Where do I like the ground the best? Where Edgar just said, right there. Why do I like the ground right there? Because the reason why is because of that current right there. That current actually makes it work just as well. So let me show you the difference between these two. Let's look at the difference. So actually, I want to go and get the thing. So the difference goes like this. So there is really no bad choices in ground. So what we want to do here is that let's look at the one Daniel said, and let's look at the one that Edgar said, and look at the fine details on these guys. Actually, let me. Okay, let's look at these. So if you look at Daniel's response, he says, no, let's put the ground right here, which is totally fine. What does that mean if you put the ground right there? What that means here is it does this. It comes in here and it says, wow, I know this node immediately right here. What is that node going to be? Well, it's going to be 4 volts. And then it immediately comes in here and it says, I know this node right here. Because if this is 4 volts and then I have that 8-volt source, then this implies here that the node voltage between, on the other side of the 8 means that this guy has to be 12 volts. Now let's go look what Edgar said. Edgar said what? He says, no, let's put the ground right here. So in this case, if this is the ground, what does that mean? Well, it changes the node voltages because now, of course, this has to be 8 volts here. And if I take my green here, you could see that this guy is now going to be what? Careful with the sign. Look at the sign. The positive is connected to the ground, so this might be negative 4 volts. So let's go count the number of unknown nodes. In each case, you could see here that I have a node right here, and I have a node right there. In this case, I have a node right here, and I have a node right here. See how they're both identical? You both have the same node voltages. By the way, if you try to compare node voltages, you'd get an incorrect, you wouldn't be able to compare the results because the grounds are different. So there's no bad choice here. You still get the same thing. The only reason why I would prefer this choice, and it's a minor choice, by the way, is because of this guy right here. When I go and I write my DC for I, the DC here, look how it's going to write here. That DC, you know, I think I'm going to go in and I'm going to define these nodes here. I'm going to call this guy V1, V2, V1, V2. This DC over here tells me that the node voltage is going to be V2 minus 0 is going to be 2I. This one is going to tell me V2 minus 4 is going to be 2I. See how these guys are cosmetic differences? So if you're struggling with like, did I pick the right node? Did I not pick the right node? Look at the difference. The equations are almost identical. The difference is this one has a -4 and this one has 0. So it's not that big of a deal. So which one am I going to pick? I'm going to pick this one over here on the right. Why? Because I calculated the numbers for this already. So this is my circuit. So my ground is going to be this one. So I'm going to move this over here, and this is the circuit that I'm going to do. So Daniel's choice was totally legit. Let's do the numbers. Here we go. So what you're seeing here is that I'm going to go through step 1. Let's do the counting. So let's count the nodes. I don't count the ground, so you can see that I got 1, 2, 3, 4. I got 4 nodes. How many sources? 1, 2, 3. Look at that. 1, 2, 3. If I have 3, let me make sure. Did I do that? I got 4. 1, 2, 3, 4. 1, 2, 3. So therefore, I only have one node equation. So that means then I go look at my voltage sources. So what kind of node equation is this? And what I'm seeing here is that the 8 and the 4 volt are connected to the ground, but you could see that the 6I source, the current controlled voltage source, or the current controlled voltage source forms a what? A supernode.
Is that why you made both of them purple?
Yeah. So then you're seeing that what this equation is that it's really not a regular node, it's a supernode between what? 1 and 2. But automatically, I have to have a super condition between 1 and 2. And then I go back and I just say, because do I have any dependent sources? The answer is yes. So I have a DC. That DC is for the I here. And then do I have to solve any variables? The answer is I have to solve. I need a solver for what? Vx. So when I look at this thing, I'm going to have what? I'm going to have 4 equations, and I'm going to have 4 unknowns. So how many unknowns do I have? I have V1, V2, I, and Vx. So those are my 4 equations. Let's go do it. So now I'm going to apply node analysis for my supernode. Here I go. So now what I'm going to start to do here is that I'm going to start to be a little bit more clever on how I write things down. Okay? So I know that, by the way, this takes practice. Okay? And if you're finding that you're doing too many mistakes, don't do this. So what I'm going to try to do here is that I know I have V1, V2, V3, oops, not V3, I, Vx, and I have my constants. So what I'm going to try to do here is I'm going to try to write these things in proper order. So here I go. So when I look at node 1, I got to write a super node, right? So here's my super node equation between 1 and 2. So how many resistors are connected to node 1? 1. So look what I'm doing. Here's my 1/2. Then I go look at node 2. How many resistors are connected to node 2? 1/2. So when I'm looking at this, do I have any currents flowing into the node? The answer is yes. I have this 4 amp source. So look where I'm going. It's flowing into it, so I got to write a +4 here. Now, look at the mutual resistor. The mutual resistor is what? Is 1/2 times 8. So that means when I'm looking at this on this side of the equation, the left side, it's minus 1/2 times 8, which is -4. If I take the 4 to the other side, I then read +4. So look what I'm writing here. So what I just wrote here is I write 1/2 V1 plus 1/2 V2. Then I have a mutual of 1/2 times 8. And then I have nothing but zeros. And then I get the 4. So look what I'm doing here. In my head, I'm moving it to the other side. So I get 4 plus 4. So I'm keeping this in matrix form right away. Then I got to go to what next? I got to go to the supercondition. What's the supercondition? Look at the high. The high is V2. So if I look at the high here, it's going to be V2 minus V1, and that has to equal 6i. Note that this is not in matrix form. So I'm going to write it into matrix form so it looks like this. So if I'm careful, look how I'm writing this thing. I'm in my mind, I'm already putting this into matrix form. So I see that it's got to be V2. Look how I go to this. V2, look how I put my 1 down. I see that V1 is at the minus. And then I look at that 6i. I know that the 6i is on the other side, but when I bring the 6i to the other side, I get minus 6i. And of course, there's no constants, there's no Vx. And I go to my DC for I. If I go to my DC for I look at this condition. And my DC says that V2 minus 0 must be equal to 2i. But I want to put this into matrix form, so it's V2 minus 2i equals to 0. So when I look at this, I know it's Ohm's law, so I would have said this is 1, and then I bring the 2i to the other side, so I get a 2. By the way, I put I there, I shouldn't have had an I. I have the minus 2, and then the other guys are 0, and these are 0. And then finally, I have the solver for Vx. So when I look at Vx, what do I see here? You could see that Vx is between node V1 and 8. So when I look at my solver, you're seeing here that I have V1 minus 8 must be Vx. So in matrix form, it's got to be V1 minus Vx equals 8. So then I'm going to come in, I'm going to write 1, 0, 0, minus 1, and then I get 8. So now I have my matrix.
Can I ask where you got the 1/2 for the V1 and V2?
1/2 for where?
For V1 and V2 for your super node.
Because I have this resistor too. And remember, it's the sum of conductances for node analysis.
Oh, okay. Yeah, I see it. Thank you.
So there's my matrix. So then what am I going to do? I got matrix magic. And I have matrix magic. They're asking for, what are they asking for? V1 and Vx, right? Or just Vx. They're asking for Vx. And if I punch this into my calculator, the Vx that I get here is 24 volts. And that's my answer right there. Okay. So, any questions? I want to go in and do mesh analysis with dependent sources. Here I go. So now we're talking about mesh analysis. And let's go look at that. So what I'm going to do here is that I'm going to focus on an example circuit. And remember, all we're trying to do is set up of how I have to rewrite the DC when I'm doing mesh analysis. So my circuit, again, is a very simple one, but it's just to really get you to see what's going on. So what I have here is that I have a circuit that looks like this. And so I have a dependent current source. This is a 100, this is a 200, and my dependent condition is this guy right here, Ix. And so what we're doing here is that we want to analyze loop analysis. So here we go. I'm going to call this I1. And then I'm going to call this, for right now, I2. I typically would never do this, but I think this is a good practice right here. The first thing that you want to know here is that look at that dependent current source. Because I have a dependent current source in this right loop and it's isolated, that means here it forces the right loop to have I2 equal to 4Ix. And I purposely picked the direction of the current of that. So what do? I don't define I2 anymore. Because that gives me more equations in the circuit. Now, some of you actually want to do that. So I would literally come in here and I would say, that is not my loop current here. My loop current is 4Ix, not I2, it's 4Ix. So what you're seeing here is that when I look at the counting, let's do the counting here. So when I look at the counting tells me what? That I have 2 loops. How many current sources do I have? I have 1 current source. Is that current source a, current source that's isolated, or is it connecting 2 loops? It's isolated. So that means I only have 1 regular loop. So what's the 1 regular loop? It's I1. But I then see here that I have a dependent source here. So that means I need a DC. So for the regular loop, it's I1. And then I need a DC for Ix. So then I have what? I have 2 equations, 2 unknowns in this circuit. So it's got to be I1 and Ix. So let's go write those guys down. So then what I'm going to do here is that I have loop 1. So let's go do, so if I do loop 1, it's going to be 200, 100. I1, there's a mutual resistor. That mutual resistor is going to be what? 100. But what's the current in that loop? It is 4ix. And then if I go around, you could see that I1 hits the positive of the 8. So when I take it to the other side, I get negative 8. So look at my equation. I have I1 and I have Ix. I have two unknowns in one equation. That's an unsolvable problem. What does the DC do for Ix? It gives me that required second equation that I need. So then I go to where the current is defined. Where's the current? It's defined through the 100 ohm resistor. Look how it's going down. Look how I1 is going against Ix. Look how 4Ix is going with it. Therefore, it says this. KCL then tells me that Ix must be the same as 4Ix minus I1. So if I do that, you could see that in matrix form, I'm going to write this as 3Ix minus I1 equals to 0. So you could see how I defined that current loop using KCL. So now, what do I have? I have Ix, I1. I now have two equations and two unknowns. It's all about the setup. So now we have a doozy of an example. This might be our most challenging circuit up to this point. And so one of the things that I'm going to challenge you to is see if you can look at this circuit before we actually solve this circuit. And what I'd like you to do is that I'd like you to understand the following thing here. What I want you to do here is that, so here's what I'm asking you before we meet next time. Do the counting. Figure out how many equations you're going to need. Okay? Figure out how many equations you're going to need. And if you have the time, go in and write down the equations. And then what we'll do here is that on Monday of next week, I'll come in and I'll do this one. I think this one's a tricky one. And the reason why it's a tricky one is that the dependent condition is not trivial anymore now. And you'll see that it's quite challenging. Okay, I got 2 minutes. So I think I'm going to stop because this is a very involved circuit. Like I said, this might be the most challenging circuit we've come up today. Okay, I'll see you guys later. And hope you guys enjoy your long time till Monday, unless I see you on Friday. Okay, take care, man.
Hey, Carlos,
Yeah,
our quiz and homework still due Monday?
no. If it's due Monday, then it's got to be switched to Wednesday. We have to do this example. Okay, thanks
Got it.
for the heads up. I will
Thanks,
change
Charles.
it for Wednesday. Okay, I'll see
All
you
right,
guys
sounds
later.
good.
Okay.